Good evening, everybody, and welcome to our WMCTC evening lecture for sixth form students. And again, thanks to the Royal Society of Chemistry and also the WMCTC committee and the University of Birmingham as well. This evening, we're delighted to welcome back Professor June McCombie, who gives a fascinating talk about the chemistry of the cosmos. A very topical talk at the moment. You've seen various aspects in the news. I won't steal her thunder, but it's a very topical talk. So please do enjoy our talk and do put any questions in the chat afterwards. So without further ado, I'd like to welcome our guest speaker tonight, June McCombie, and invite her to share her screen.
Okay, so many thanks to WMCTC for inviting me again to give a talk to the A-level students that they attract to these events. You've always been a fantastic audience in the past, and this is a new way for us to interact, but as I said to Mark, at least we aren't struggling to get to Birmingham University at the moment or to leave it at the end. So my job tonight, I'm going to talk to you for about 45 minutes, and my idea is to give you an idea of the range of chemistry that is taking place around stars and in the space between stars in the interstellar medium, and to convince you of the importance of having information on this chemistry. So molecules are formed in most places in the universe that are cooler than the sun. But in particular, they're abundant in molecular clouds. In the dense regions in these molecular clouds are the places that they're the nurseries of new stars and planets. I'm going to talk from the chemist's point of view, but molecules are important to astronomers as well, because what they can be used to do is to trace remotely and probe star and planet formation. So if you think about a molecule that's in a particular physical environment, the light it gives off or the light it observes tells you something about the pressure and the temperature of the environment, or maybe any shocks that are happening. It might be fragmentation, etc. So this information feeds into the astronomer's toolkit as well as into the chemist's toolkit. So just to give you a bit of information about how I ended up doing this though. So my background is actually as an experimentalist working in high resolution molecular laser spectroscopy. That basically means that for a considerable period of my career, I spent most of my daytime in rooms with blackout blinds and in the dark. Blackout blinds because you couldn't risk hurting anybody passing outside the room because you're using a laser. Blackout blinds so that you could actually align the laser on your desktop. So here, I'm just going to try and use the laser pointer here. Here you can see a typical setup that I used to work with. So I would take laser light and I would use it to probe molecules or aggregates of molecules, clusters of molecules. And by either the light they absorbed or the light they gave out, I would be able to say something about their structure and their kinetics and maybe their floppiness, etc. But I learned a toolkit of spectroscopic techniques, and those are equally, well, those are applicable in a number of areas of science. And astrophysical chemistry research, I was lucky enough to be actually had an office next door to somebody who was an astrophysical chemist who said, look, could you look at the spectra that I got using a telescope? And that got me hooked into that area of work, with the added advantage that the students loved it. So that was pretty good. And that led me to, I still seem to work in very dark places, but here is the United Kingdom Infrared Telescope, which I did some work in, and down at the bottom here, we've got the plateau, a plateau of the Karoo Desert in South Africa with a number of telescopes, and I also spent a considerable amount of time working there. And scattered around on other places on this slide are just a few examples of, well, there's a teaching lab in the University of Nottingham, very much I imagine like a teaching lab in the University of Birmingham, but here's an object that I used to work on, the red rectangle. Here's some spectra I observed, and here's a molecule I did a little bit of work on. So that's me. But let's get back to what I need to talk to you about. So this is obviously something of a cartoon, but what I'd like you to note is that here, if I, it's a cartoon, so dawn of time, and then we've got what the universe looks like a fraction of a second later. What you can see that it's quite homogeneous, a fraction of a second later, all right? And then we have a period of inflation about 400,000 years later. This picture is actually the cosmic microwave background, so it's a spectra taken by cosmologists. And you can see that there's some structure and spatial differentiation coming in, but then if we come to now, we can see that we've got a local universe that's quite complex dynamically, very highly structured. So one of the curious things is that we can actually, in a way, we better understand what happened in the combination era of the universe than we do than we understand star formation in our local universe, because of course at the moment, because there's so much variation, both dynamically, structurally, temperature-wise, pressure-wise in our local universe. Whereas a tiny fraction of a second beforehand, we actually had very small perturbations taking place. So basically, when the universe cooled down enough for electrons and nuclei to combine, neutral atoms started to form. And in the standard model, nucleosynthesis occurs in about the first 180 seconds of the history of the universe, whereas galaxies form at about 10 to the 9 years, and we think of stars as occurring in the present. So putting it really simplistically, Big Bang producing a universe rich in atomic hydrogen, helium, and a tiny amount of lithium. The appearance of those neutral atoms led to the formation of very simple molecules and molecular ions, and I mean simple, H2 plus, H2. However, at that initial stage, the abundance of these small molecules remained small, and it was constant because they had very small rates of formation. And so that kind of begs the question of how the richness of molecules that we now see came into being. But the richness of molecules that we now see was not always an established fact. So here you've got the chemist's periodic table, right? So you've got these in your chemistry books, and I'm sure that in your school rooms or in your school labs, you'll have one up on the wall. And this is not even up to date, actually. Far more have been discovered since. But this is the chemist's version of the periodic table. If you go to an astronomy textbook, what you will see is this. Right? So in an astronomer talks about metallicity. And they define whether you're in a high metal region or a low metal region, depending on the ratio of the metals, as shown here, compared to the amount of hydrogen and helium. And so, within an astronomy world, since you had hydrogen and helium, the metal, and then just metals, going on to say, well, how about the molecules, is quite a step. And you will still see this in the majority of standard astronomy texts. So for many years, it was thought that molecules couldn't survive the harsh environment of the interstellar field. And it wasn't until some 80 years ago that spectroscopic observations in the visible and near ultraviolet began to show otherwise. The technology developed. You had telescopes that with large enough mirrors to have the sensitivity to look at spectra that molecules were producing, and the resolution, so that you didn't just see a big blob and you couldn't say what molecule that was due to, but you could see sort of smaller blobs. And so you could say, well, that's water and that's carbon monoxide. But this is Sir Arthur Eddington, who was the Astronomer Royal in his day, and he made the statement that molecules cannot survive the interstellar radiation field. Well, we now know that they can. So again, this is incomplete because there are now hundreds of molecules that have been detected in the interstellar field. But here we have some examples going up to some slightly more than 6 atoms of different molecular species that have been observed. I mean, there's something close to now over 300 molecular species that have been observed. And probably when I say observed, I mean assigned. So where we could definitely say that this spectral feature corresponded to this molecule. Far more than that number will have been observed, but unless you can obtain a spectra in a terrestrial laboratory, which you can then match with the one that you've taken in a star region or in interstellar space, you can't really do that identification. And there's some very exotic molecules, we think, in interstellar regions or in stellar regions, which we can't stabilize on Earth. They're not, they fall apart very quickly. You have to be looking at them as single molecules, which requires quite a lot of experimentation. But here's some of the more abundant ones. So we've got hydrogen, we've got water, CO2, methanol, some of the carboxylic acids, ethanol, and of course things like glycine, the simplest amino acid, which has now been observed. And as I think I said before, the buckyballs have been seen in some areas as well. And those are very large, you know, carbon-60 molecules, or the fullerenes even. But such large molecules are very stable because of their symmetry. And so they give extremely weak signals, but they're extremely stable. So, but once people started to observe these molecules and they could see that they pervaded across interstellar space, people wanted to understand their formation mechanism. And it was later realized that there were regions of space that were actually forming stars, and these were also rich in complex molecules. And that implied that there was a link between the two phenomena, between the richness of the soup in the interstellar region and the fact that you had regions of space actively forming stars, which were also rich in complex molecules. And so, in fact, molecules actively control star formation. Without molecules, especially the small ones, such as hydrogen, carbon monoxide, water, the universe as we know it might not exist. Despite these identifications, there's still many factors weighing in against chemical processes, and that's probably what I want to probe with you. But let's just give you a quick picture. This is an image of part of the Orion Nebula, and you can see here this, you know, this is wavelength along this scale here, and here we see the identifications of a number of small molecular species, which you're all familiar with: sulfur dioxide, carbon monoxide, water, methanol, acrylonitrile, methyl formate, etc. So a pretty picture. But let's go back to star formation and chemistry. So this is M16, and what we're seeing here, if you look at these little red blobs here, right, those are stellar eggs emerging from a molecular cloud. And this is a Hubble image, and what you're really seeing is the shadow that the dust in the molecular cloud is presenting. But okay, so star formation and chemistry. Now I've got to convince you that chemistry plays a part. So let's have a look at this slide. Here we've got, just look at this top line here. Here we've got a cold hydrogen cloud. So we've got the simplest composition of a molecular cloud that we could have. The cloud is undergoing gravitational collapse. As it undergoes gravitational collapse, it's getting compressed. And as it's getting compressed, it heats the gas up inside to very high temperatures. And certainly in the initial round of star formation, that would be to above 1000 Kelvin. So, and at these temperatures, the motion of the atoms in the gas begin to resist the force of gravity that's making the cloud collapse. Think of if you pipe up a bicycle tire and you increase the pressure in it, if you put your hand on it, it's warming up, okay? So at this point here, what we've got is the atoms in the gas beginning to resist the force of gravity that's making the cloud collapse. But unless it continues to collapse, we're not going to get the star. So the question is, how did the star formation happen? How did we get to the cloud to cool? How did that cooling occur so that we could make this transition from this hot hydrogen, this molecular cloud that has a hot hydrogen clump in the middle, to the star formation itself? So at the time that the cloud was collapsing, the hydrogen atoms in the cloud were forming molecular hydrogen. So because you're heating them, and actually, as you're increasing the pressure in there as well, you're going to get some formation of molecular hydrogen. This molecular hydrogen cools the gas in the star forming regions by emitting heat in the form of microwave and infrared radiation. So as the hydrogen molecule rotates and vibrates, it emits microwave and infrared radiation so that it can cool the temperature of the cloud down, and it cools it down to around 300 Kelvin. Now that's still a lot hotter than the molecular gas cloud that forms stars today, but let's assume that this is the first cycle. So we're going from 1000 Kelvin up to this point here, we're cooling the clump down to around 300 Kelvin, and we form the star. Now, the reason that that's hotter than the molecular gas clouds that form stars today is because we now have many more molecules and dust to help cool the cloud. This line here is just to give you an example using carbon monoxide, and these J numbers here. J is a quantum number that you can give a molecule, and the J quantum number tells you something about how fast it's rotating. So if it says J equals 0, it's not excited at all. If it's J equals 1, it is excited, but then because it's excited, it can emit radiation and drop down to J equals 0. So it's collisions at this stage that are pushing it up the energy ladder to J equals 1, and it's radiation here that it's dropping down to J equals 0. Now this is just carbon monoxide. As you go through star formation cycles, then you're getting more complex molecules in your molecular clouds, and the more complex molecules have more types of vibration and rotation that can be taking place, so they're much more efficient at cooling the molecular cloud than would be hydrogen or just CO. So that's the star cycle. It's the first phase of the star cycle, and of course the other phases are when the stars end their lives. And the most massive stars, this one's the Crab Nebula, undergoing a supernova explosion, and what we're seeing here is the supernova remnant, and that's quite a sort of instant process. But less massive stars like our sun, they die more peacefully, over thousands of years, shed its outer layers. But whichever mechanism, be it supernova explosion or this peaceful shedding of the outer layers, what they're doing at that point is putting their matter back into the interstellar region to repopulate the molecular clouds, and at each cycle you get more complex molecules. So what we have essentially is we have a universe dominated by physics at the time of the Big Bang, but over the last 15 billion years, what we've got to is a chemically controlled cosmos. But there are still some real puzzles or there were some real puzzles until about 1993 for a chemist thinking about the complexity of molecules that we are observing in space. Because what we did know was a couple of things about the environment in these interstellar regions and in these molecular clouds. And particularly in the interstellar space, we know that it is very cold, right? Around minus 263 degrees centigrade, so only a few Kelvin in temperature. Now here's a standard sketch. You've got energy on the y-axis and you've got distance apart of, in this case I've drawn it as being atoms, so, but it could be molecules, right? So distance apart in your molecules. So you've got your molecules coming together. They come together and they've got to get over this activation energy barrier in order to react. Now, this is standard when you're in your labs and you're asked to conduct a experiment where you're making two species react together. You're normally adding, let's be simple, species A and species B, my favorite two species, and usually they're probably liquids in your case, they're not in the gas phase, and you pour them into a beaker, right? Now, unless you have, and those will be neutral molecules. So those neutral molecules somehow have to get over that activation energy barrier. And the way you do that in your school laboratory, I'm pretty certain, is you get out the heating mantle, right? And you apply some heat, and that gets them over the activation energy barrier. But at minus 263 degrees centigrade, they are not going to have enough thermal energy to get over that activation energy barrier. So, some energy has to be put into them to make them proceed, and that's just not going to happen from the thermal environment. So there are some reactions that have almost very low or no activation energy barrier. Usually those are not processes that involve simply two atoms or molecules. Sometimes if you've got a radical or an ion and a molecule, there'll be very low activation energy barrier. But sometimes they have to be collisions involving three chemical species so that the third species stabilize the newly born molecule in those few reactions that occur without activation energy barriers. And that, of course, brings us to another thing about interstellar space, and that's the fact that it's at very low pressure. So, you know, what's the easiest way to get a reaction to take place? You have to have the things collide, right, to start off with. Now, if you're adding liquid to liquid, you've got this intimate mixture of your A and B. It can also occur in the gas phase. You have reactions taking place in the gas phase. But let's for a moment think about what the atmospheric pressure is in the room that you're sitting in, right? It's around 1,000 millibar. Pressure in interstellar space is around 10 to the minus 15 millibar. So what does that mean? Well, the pressure is extremely low. Chemical reactions go slower as the pressure is reduced because, quite simply, atoms and molecules have to collide in order to react. And at very low pressures, collisions are highly unlikely. Now, I've given you that in terms of pressures there, but what does that mean in terms of number of particles in a given volume? So this is a dice, right? And roughly 1 centimeter cubed, let's say. And at atmospheric pressure in your room, I think I put 19 on this. You've got 10 to the 19 particles at atmospheric pressure in that cube. If I go to the dense molecular clouds, and some of you may also have heard of diffuse molecular clouds, but in dense molecular clouds and star-forming regions, you've only got about 300 particles in that 1 centimeter cube. So that means that those reactions are going to take place very, very slowly by comparison with what with taking place in a terrestrial laboratory. So what's the best way to make something happen? And that is to get a number of atoms or molecules in one place. And so in the last few years, since about 1993 was when some dust was first confirmed as an observation, and then later, slightly later, there was another mission that reconfirmed it. But so let's say astrochemistry as a discipline has probably only been really active for the last 40 years. So in the last few years, last 20 years, astrochemists have come to realize that this new chemistry has to occur on the surfaces of interstellar dust grains, and that dust grains play really key roles in the chemistry of the interstellar medium. I kind of gave it away earlier on because I wasn't just talking about molecules, I was also talking about dust. But actually the dust wasn't really observed until 1993. So grain surfaces give you you can catalyze the recombination of atoms to form simple molecules. And then if you form very volatile molecules such as hydrogen, they can desorb from the grain surface and they go back into the interstellar medium. Less volatile molecules such as water, ammonia, methane, they accumulate as solid ices on the surface of grains, and they condense solid. When I say ice, then it's not just water, ammonia, methane, things like that. And then in the coldest regions of the interstellar medium, other gases can condense on the surface of the grains and add to the chemical richness. And then in those grain surfaces during star form can be processed by things like cosmic rays impinging on them. And then during star formation, those icy grains are warmed up and they release these molecules into the gas phase. And it's a very complex process. But once their molecules are returned to the gas phase, they help radiatively cool this collapsing clump of gas as it moves towards becoming a star. And also for the astronomers, they can significantly perturb the gas phase chemistry that's happening at the core of that collapsing clump of gas. And they act as markers for different phases of the star formation. And that's where some of the interest comes for the astronomers. I only have that animation in my slide. So this is it, showing you the hydrogen forming on a dust grain, a very flat dust grain. And as I said, interstellar dust first discovered by German-made dust detectors on the Ulysses spacecraft in 1993, later confirmed by the Galileo mission to Mars. So here's my hydrogen forming. This is all I was capable of in terms of an animation. And there it forms, and there it's extremely volatile, there it leaves. So surface reactions are also thought to account for the formation of ices, and once formed, the ices are processed in various ways by light and by heat. And that leads to these amazing cartoons that people have put together showing you've got young stars, we've got dust and molecular cloud, you've got shock wave, shock material. Here I've got a silicate core, I've got molecules forming around, condensing onto that silicate core, onto the dust grain. Those molecules are then processed, and then they, as they're heated up, they then eject the molecules back into the interstellar region and into the molecular clouds. So 1993 for the first detection of dust within our galaxy, but it's not limited to our galaxy. This is NGC 891, and it was thought to be very similar to our own Milky Way galaxy. This is seen as a spiral galaxy, seen at edge on, but fairly recent high resolution images show these filamentary dust patterns. And I'm not showing you this picture because it answers any questions, but just as an illustration, sometimes you get newly discovered phenomena that is so complex that it raises more questions than are answered, because dust is extremely fragile. So the fact that you can get these filaments of dust surviving disk expulsion, there has to be something new happening. We don't know. We don't know. So let's move on, though. Let's move on to how we detect these molecules and what they can tell us about the environment in which they're found. Well, you've all seen this picture before, I think, or a version of it. Okay, so here is the electromagnetic spectrum, and what we look at is chemical fingerprints. So spectroscopy is basically looking at chemical fingerprints. Here's the visible light region, here's the infrared, here's UV, and you've got gamma rays going right the way through to AC circuits. Okay. So light tells the molecular story with information on the formation and evolution of stars and the roles of atoms and molecules. The problem with molecular astronomy is knowing where to start and where to finish. All right. So if we think about molecular astronomy, the laboratory-based big brother of it is high resolution laboratory spectra. And it's the synergy between the high resolution laboratory spectra and molecular astronomy that allows us to identify molecules in space. So here we have a picture of the Orion constellation. This obviously was taken by the Hubble Space Telescope Orion Nebula team, and you can see a large amount of detail there. But even if you look with your own eyes, or with a telescope that you can have in your garden, right, you can see a bit, right? But we're only seeing with visible light. Okay, so this is the Orion constellation, and you can see a bit, not too much. But this is what you see if you look through a thermal imaging camera. And what you can see here is you've got the Orion constellation, but here, down here, we've got the Orion Nebulae, which is the closest region of star formation to Earth. So to give you an example of the spectra you might observe from this region, here is spectra taken of carbon monoxide. So there's it was looked at in two different regions of the Orion Nebulae, and I'm not going to repeat the names of these regions. Astronomers have long descriptive names, but let's just call them region A and region B. Up here, we have intensity here on the y-axis and wavelength on the x-axis. And up here, we have a simulated stick spectra for carbon monoxide gas, just the gas. And what we can see in the stick spectra is we have these lines, they're fairly reasonably evenly spaced, and then we have a gap in the middle. But when we look at the spectra taken from these two positions in the Orion Nebulae, what we can see is that we've got carbon monoxide, we've got a very deep dip here, a strong signal in both cases. And this corresponds not to carbon monoxide that you would see in the gas phase, but carbon monoxide that you would see if it was sitting on an ice surface. So if a molecule vibrates at a certain frequency, that would correspond to one of these lines here if it's in the gas phase. But when you put a molecule on a surface, the interaction with the surface means that that frequency changes. And so you shift the spectrum. And so here we see the spectrum forming where we would expect to see it for carbon monoxide sat on ice. And that's what we get there. Now, obviously, you've got lots of fancy kit to get these kind of spectra. And here are just a few examples. Atacama, the Sophia, Herschel, ESO's very large telescope at Paranal in the northern Chile, and this is in the Atacama Desert, possibly the driest desert in the world. And this is probably the world's most advanced ground-based facility for astronomy. This is just showing you ESO. They have a number of other telescopes there. And dry is important for a number of reasons, because of course the atmosphere will absorb light that's coming towards any ground-based telescope. So you want to be high and you want to be dry. And then I want to show you the NASA James Webb Space Telescope. This was a picture taken in 2017, but you've all heard on the news recently about its launch, which was frequently delayed. I did get to see the primary mirror. This is a picture of the primary mirror before it was shipped out to Houston. And so people say to me, well, is that going to be useful for chemists? What are we going to see? Well, if I go back to one of the starbirth clouds in M16 and think about James Webb Space Telescope for the chemists, part of the science case were when people put together simulated spectra of what they expected to see of in terms of molecular spectra using the James Webb Space Telescope. And so this spectra here is a simulation of what it's hoped will be seen in that M16 nebulae, the Eagle Nebula, showing water, methanol, carbon dioxide, silicates, and so on, using the James Webb Space Telescope. So it will have the sensitivity and the resolution, and it's a large telescope. It will have the sensitivity and resolution to give us molecular spectra in areas where we haven't been able to look before. But okay, so if I've told you though that what we need to do is to match lab-based spectra with telescope-based spectra. So the question is, how can we recreate the interstellar environment and study things like ice chemistry, the chemistry happening on ice surfaces? And here are two bits of kit taken from an astrochemist lab. And what you can see is large pumps, lots of stainless steel, and light sources. Here's the light source here. Because reproducing space in the laboratory, well, that means getting to low temperatures and low pressures. And you can't quite, temperature one can get down to. One can get down to the temperatures in interstellar space. Getting down to the low pressures is more difficult, and it mimics the denser regions of the interstellar medium associated with star formation, but we're not able to mimic the sort of the diffuse regions of the interstellar medium yet. But we can get down to around 10 Kelvin using closed cycle helium refrigerators, and we can use tools such as infrared spectroscopy and temperature programmed desorption, coupled with mass spectrometry to investigate what's happening. And so this application of surface science in laboratory astrochemistry is new and it's exciting, and it's made a lot of contributions to our understanding of chemical evolution. So the kit is relatively complex, but the experiments taking place are not a million miles away from what you might do as a student, right? So here we have, let's just assume this is carbon monoxide. We have a surface here, and it would be something like a diamond crystal, possibly with some ices laid on top at around 10 Kelvin. We sort of have a gas flow of carbon monoxide going down onto it, so that carbon monoxide molecules stick on the surface. We bring a photon in, we hit it, and we see what light it emits. And from that, we can say something about how it's attached to that surface, what the strength of that attachment is like. We can also take the surface, and after we put maybe we put water on there, maybe along with a little carbon monoxide, maybe some methanol, and we can then heat the surface up and look at the molecules that are ejected from the surface. So what would go back into the interstellar medium? And you can analyze these using techniques that you've been introduced to, either been introduced to as A-level students or might be introduced to next year, depending on where it comes in your curriculum. But now you do look at mass spectrometry as A-level students, and here's a very simple mass spectrum of CH4 of methane. And a mass spectrometer is basically a tube that where you take your sample, you ionize it, and the lighter ions arrive at the detector first and the heavier ones later. And so you can build up a spectrum that has abundance on the y-axis and mass overcharge on the x-axis. And this use of mass spectrometry in space has allowed us to answer a number of questions. So, did this meteorite come from Mars? Are comets mostly made of water? Are there amino acids in comet dust? Are there organic molecules in Titans? The answers to all these questions, which is yes, by the way, for all of them came about by applying mass spectrometry within your study of meteorites, comets, comet dust, the atmosphere of Titan. And mass spectrometry has been used widely because another branch of astrochemistry is looking at things like doing sample analysis at Mars. So here's a Mars rover, and here is the relatively small instrument on a Mars Science Laboratory rover. So it's quite small. You can tell by the heights of the scientists alongside. And so this comprises a mass spectrometer, a gas chromatograph, and a tunable laser spectrometer. So that's quite a technological feat to get all of that equipment with reasonable resolution into a piece of kit that size and to make it robust. And it takes up more than half the science payload on board the Mars Science Laboratory rover. Other things are the Rosetta mission, first detection of molecular oxygen at a comet. And actually, I just want to finish by saying, you are all able to be astrochemists without too much effort, actually. So Comet Swift-Tuttle in 2017, the Perseid shower, all right? So you are all seeing some chemistry going on here, because what you've got here is the comet, and what you can see here is you've got a nucleus here, and you've got two tails to it, and those two tails have different colors, right? And they're spatially separated. And if you were lucky enough, you could actually get some idea of that when you looked at the Perseid shower. And so the nucleus here is heavily carbonaceous. But if we come here and look at the ion tail and the dust tail, the ion tail is composed of what you'd expect, ions. And the thing is that it's because they're charged ions, then as the comet comes through the solar wind has its own magnetic field. And so it deflects that ion tail away from the neutral dust tail. And the blue color is because you've got primarily charged ions, primarily CO+, and CO+, when it emits light, emits it in the blue region. So if you've seen that, you've done a little bit of astrochemistry observation all of your own. And the same goes along with if you're ever lucky enough for driving up to Scotland or going to Iceland to see something of Aurora Australis and Aurora Borealis, these ribbons of red and blue lights that occur in the sky. These are 100 kilometers in the vertical axis, a few hundreds of meters in thickness, but they are again caused by radiation of light from different atoms and ions. So the auroral light is mainly from excited oxygen atom, and green radiation at low altitudes and red at higher. And there's some nitrogen molecules and nitrogen molecular ions that produce red and pink at low altitudes. And the reason you're getting green radiation at low altitudes and red at higher has something to do with the lifetime of the excited atoms and excited ions. So I will stop there and just say to you that, I think there is no more amazing chemistry happens in space. I'm still amazed by it. This is an artist's concept of buckyballs against the backdrop of the Small Magellanic Cloud, which was imaged by the NASA Spitzer Space Telescope, where they observed buckyballs in space. And I can think of no firmer proof that amazing chemistry happens in space than that. So thank you very much. And I will stop sharing my screen there.
Esther, thank you very much for a really interesting and thought-provoking talk there. Some of these images are amazing, and it is incredible sometimes that science is actually more strange and beautiful than science fiction. So thank you for that.
That's true.
As ever, if anyone has questions they'd like to pose, please put them in the chat, and we will put them to our speaker. I mean, the spectroscopy is a fascinating part of it, and when the RSC had its spectroscopy in a suitcase, it was great, and I was able to, on a couple of events, visit the Space Centre up in Leicester, the National Space Centre, and there they've got some really interesting information, well, about the Hubble telescope and the role of spectroscopy on board there. So again, if people are interested, certainly going to have a look at some of those examples.
Yes. I mean, and the Leicester Space Centre is amazing, and you can have a lot of fun there whilst learning a bit. But they have some, they have some remarkable examples there. So, go on, don't be shy.
As I was going to say this, I don't know if all my settings are correct, but I'm not having any questions coming through.
Maybe somebody could just type in question mark, just so that we can check that the chat's working.
Yeah, please do. So it does here say allow participants.
We won't ask you to ask a question if you do that, I promise.
And they can chat with the host and the co-host. So nothing's coming up so far. I'll put everyone there. I mean, while that's happening, if there are people that are studying sort of A-levels at the moment that are really inspired by the kind of astrochemistry and the sort of research that you're doing, what advice would you give them in terms of pursuing that through sort of degree and higher level? What advice would you?
Yeah, I came in through a slightly, well, not a particularly unusual route for my generation. Cheyenne, yes, I will answer that, I promise you. Through not a particularly unusual route in that astrochemistry didn't exist when I was a student, right? There was no such discipline within the UK, to the best of my knowledge. So in terms of pursuing A-levels, keep going with your chemistry, your physics, and I'll plug the maths. Please keep going with your maths. But there's obviously interest as well. Now there's astrobiology, and there's a number of biologists working in the sort of astro area as well. But in terms of degrees, I'd say that if you can, some people will want to take an astrophysics degree. which you can do in a number of physics departments. Either offer separate astrophysics degrees, or you can do physics with a possibility of specializing in astrophysics later on in your degree course. There are fewer places doing astrochemistry as a degree course, certainly in the UK. But there are quite a few departments where you would have the possibility of doing astrochemistry as a third or fourth year project in your final year. But there are also Leiden University is a fantastic venue for astrochemists. And so, there is there is some possibility of the rest of Europe as well. So Cheyenne, I hope I've pronounced your name correctly, has asked me to recommend any particular books, websites, or resources to learn more about astrochemistry. If you go into Google and you type NASA astrochemistry, NASA has a substantial astrochemistry group. And it is a great website because it gives you a multitude of links to other groups, both in the US, but also in UK and Europe, who are working in that area. The other place to go to is if you Google Leiden, L-E-I-D-E-N, Leiden Astrochemistry, which is in Holland. They have one of the biggest European groups working on astrochemistry. In terms of particular books, there are a couple that I would recommend at an undergraduate level, but they are quite specific. But there is a book called Astrochemistry, written by a woman called Claire Vallance, V-A-L-L-A-N-C-E, and that's one that I used when I was teaching an undergraduate course in astrochemistry, which was very popular amongst normal chemists, if we can call ourselves normal. But I would go to the NASA website because they're great at updating it, and they're great at giving links to other groups.
So I have a question here regarding travel. It's interesting. I think your pictures of the telescopes and the South African plane and all these exotic places. Someone's asked, do astrochemists get to travel more than others due to the fact that the groups are spread out around the world? You used to get to travel a lot to get your data. So I used to, certainly for the first 10 years when I was working as an astrochemist, if not 15, I would do the observations myself, by and large. So this was on ground-based telescopes. So, it's a peer review process to get time on these telescopes. There was one where I was told, and it scared me awfully, that it apparently cost £20,000 a night to have me at the telescope. So that's in terms of the sort of financial support that had to be there for the telescope to exist. So if I was given 2 or 3 nights on it, which might have been all I had that year, that was still very expensive. Now, I didn't pay that. My university didn't pay that. The research councils paid that money, but it was a peer review process. So you put in a scientific case and a technical case, and about every 6 months, there's these grants applications are reviewed, and if you get the time, you get the transportation money as well. But more and more nowadays, they have moved to remote observing, which means that you basically sit, and this is long before COVID, you'd sit at home on your computer, and you would be deciding on the parameters and the steering and so on online with a support scientist who was full-time at the telescope. Now that's a shame, and it's a shame.
And to be honest, astronomers have always done a lot more online collaboration than maybe some other scientific groups, because you would only ever have one or two of you at a telescope at best. You didn't have a laboratory to congregate in, and quite a lot of the projects are big projects, so there might be a consortium of 20 different groups working on something. Certainly with the Herschel, with HST and with Spitzer, which are, but neither of them background based, but obviously if it's a satellite mission, you're never going to get to go there, are you? So you're going to be collaborating with a large group, and the data answers many different questions, so it can be interpreted by in many different ways by people looking for different information. Somebody like me might be looking for the molecular spectra. Somebody else might be looking for a wavelength shift that indicates shocks in the area. Somebody might be looking at sort of galaxy formation, history. So I don't know that we travel more now. We certainly used to, but I think that has died off a bit. I can see Justin has asked, exoplanets determined in planetary atmospheric composition, how far from the star would a planet have to be? I cannot answer that one. Have to be so that the telescope can separate its spectrum from that of the star. It is done basically on differences though, Justin, sort of planet in front and behind the star. I must admit differences between the spectra. I have to admit I don't know how you would. Ooh, I don't know. Yes, I can't give you a number on if it was to be looked at in a different way, but the exoplanets, you're looking at something transiting. So you're looking for the difference between the two spectra.
Actually, Jeff, I may, you mentioned the kind of role of sort of remote access to telescopes, the data. Have you been involved in any projects where they sort of linked various telescopes together to get a sort of larger
Yeah.
data? I've obviously.
Well, yes, I mean, a lot of the radio data is done that way because of the mixing. So if it's, the square kilometer array, for example, is a number of heterodyne detectors over a vast area, right? And somebody a lot more technically minded than I would have this, the pipeline, it's what you call pipeline processing of that data. And so it is more, it's very common when you're looking at radio spectroscopy. There's a little bit that goes on when you looking at sort of matched telescopes in different parts of the world. I mean, that's partly because, well, it's partly that you can see an object at different times of the year from different sites within different telescope sites. But there's there's a lot of problems with certainly any work I've done like that when you've been using a ground space telescope, getting your baselines the same is very difficult. So when you're taking a spectra, you don't just sit looking at your object, you have to do what they call nod away from it on quite frequent occasions in order that you can, because the atmosphere around between you and your object is changing with weather conditions and with time as you're sort of moving, as it's moving around within your sort of your window of sight. And so you have to nod away quite frequently so that you can subtract that sort of atmosphere, sort of background spectra, if you like, from your spectra of your object. And so the worse the the more turbulent the atmospheric conditions, the more frequently you have to nod away. And so whenever you're making a technical case, it's not just for, I need this amount of time on my object because I need to have that intensity of signal. It's, I've also got to add in probably 2/3 of my time actually looking away from the object in order to do that. And you literally swing the telescope away.
I can imagine it sounds great in principle, but I can imagine the practicalities. There's a lot of time and effort trying to sync everything.
You have some fantastic support scientists, telescope operators. Some of them I worked with, had spent 20 years working with a telescope. They knew it backwards, and they were very kind about making you not feel stupid. They were really very good about that. But then you had support scientists who, again, possibly didn't know the nuts and bolts of the telescope in quite the same way, but they knew all about how you were going to have to take their data and put it through a pipeline in order to reduce it, in order to look at it. And so they were very clear about what you needed to do in order to clean up that data. So they're the real heroes of the telescopes, basically.
So being an astrochemist, as well as chemistry, spectroscopy, maths, I presume you also need to do a bit of programming or data manipulation.
Yes, data manipulation. It used to be programming, but now quite a lot of the data arrives to you having gone through these pipelines. But you certainly need to know enough to be able to use a black box intelligently. And so the data manipulation, the data reduction is, but you work in groups, and so you may not have all of the same, you don't have to have all of the skill set. You have to have an appreciation of all those areas, but you might be the expert in one area and another person in your group is. I relied enormously on some really great PhD students who knew all about the data processing, and spent longer on it than I did, basically, because that was their job for 3 years. Mine was doing a bit of teaching, a bit of admin, and a bit of research. So they spent longer on it than I did. And I would say to any of the students on here, if you go into a physics or chemistry department and you are thinking that you want to do more in this area, try and get a summer project with somebody working in this area, just to get a taste, even if it's only for a couple of weeks. Just get a taste. And there are some summer schools that are run by some of the larger universities, which will take on a number of students and work with, train and give you a mini research project over a period of time. And yes, they're very competitive, but if you never ask about them, you're never going to get them. So always try.
That's very true. That'd be great advice if you can get them, certainly. You mentioned earlier about your sort of role in outreach and various other outreach projects that are going on. Is there any sort of outreach that people can get involved with within the Midlands region at all? Is there anything that, if someone is interested, is there any way they could sort of look something up or get involved with any outreach?
I think there will be. I think it's sort of not been happening for a while, or at least the outreach has sort of gone online, if you like. But there are certainly, I know there are programs at the University of Birmingham and the University of Leicester and the University of Nottingham, which are all in the Midlands region. I mean, if you, at the moment, in a way, the students on my screen, I think you are the ones people are trying to outreach to, in a sense. But what I would say is that once you make the next step, or even if you're, if you decide you're not going to go to university, you want to do something else in the meantime, the Royal Society of Chemistry runs various schemes whereby students and young people in general, and forgive me for calling you young people, but you know what I mean, you're considerably younger than I am, young people in general can get involved in outreach. And you have RSC educational coordinators, and I have to admit, I don't know I know Heidi Dobbs in the Nottingham region, and I have completely forgotten who it is over in Birmingham, but I'm really sorry. But there are Royal Society of Chemistry educational coordinators who run outreach events, and usually looking for volunteers. So if you go on and you Google RSC educational coordinators, it pops up with a list and you can find out who's relevant in your area. Anushka, no is the answer. I think it's great you're getting a telescope for your birthday. What to look and when choosing one, I cannot, but what I would say to you is find your nearest amateur astronomy group. And go along to one of their events that will be held in an evening. Now there's, because I occasionally give talks to them, so I know there's a great group in Chesterfield, there's a great group in Nottingham. I don't know about the West Midlands because all of their talks are late evenings, so I have this thing about I have to be able to get home in the same day. But I would go to a meeting of whatever local amateur astronomy group you can find, Anushka, and ask them, because they are the real experts on this. Okay. And in fact, what I do is I'm about to sign up actually to join one of the amateur astronomy groups, because I very rarely get to look through like a telescope with my eye. I'm always sat on the end of a computer screen. So I would go and find your local, thank you, Justin, Shropshire Astronomical Society. And they would love to see you and give you advice. I'm really certain. And they may be able to sort of let you try out a few before you see what's out there.
Listen, thank you. I didn't have any questions on mine. Apologies. I don't know whether Zoom has changed its settings, but I used to see all of the chats in the chat box as the host, but I can only see ones that are directly addressed to me. So I do apologize. So I used to see them all. So I'm afraid I haven't got any more, but has any other committee members got any other questions in their chat box that hasn't been answered yet?
Oh, Trevor's got one.
Trevor's got one.
Go on, Trevor.
My question was going to be, has any astrochemistry experiments ever been done on the International Space Station?
I don't know about the International Space Station, but certainly on Sophia it has, on the zero gravity. So there's a woman called Helen Fraser, who works at the Open University, and she's done some zero gravity astrochemistry experiments on Sophia. But I don't know about the International Space Station. But if you look, okay. I would look up her website. So Helen Fraser, Fraser, at the Open University. And I think she will have that kind of information.
By the way, I've just looked up on the laptop astronomical groups in the West Midlands, and it's come up with about 12.
There we go, Anushka. If you Google, you'll find the one nearest to you, and there are really friendly groups. I would dress up warmly for the visit, because it's normally sort of late at night, it's cold, and they have to keep you have to keep the telescopes cold. You can't heat the domes. Apart from the expense, it distorts the mirrors and the focusing. So my best advice is go along, but dress up extremely warmly. Trevor?
I was also going to say that there are one or two areas around the country that have got what are they called? dark areas?
Yeah,
where there's
Kilda,
light blue? Kilda.
Kilda Forest I think is the best known, and I was thinking of trying to get up there later this year. And there was a very good program on it. I think on BBC, but I'm not certain. A few weeks ago. So the Kilda
Well,
Forest.
My brother-in-law went to one. I think it was Kilda, and there were hundreds of people there with telescopes.
Bit more
Amateur.
expensive than just nipping to your local amateur
Of course,
astronomy society. Yeah, but yeah.
Good night out.
Listen, so I don't have any other questions. Are there any other questions from the committee members?
Some of them have heard this talk so many times that they really cannot ask any.
Well, in the absence of that, I'd like to thank June so much once again for a really interesting and engaging talk. I don't know if Jill wants to echo some comments from the chair and a formal thanks.
Yes, I would just like to thank June for once again speaking to us. We're still ashamed that we can't meet in person, but it's marvellous that we can meet online. And although I have heard it before, as June said, there are always things, whatever our age, we are learning. And I was quite fascinated by how I'd never thought why the iron trail was separated from the dust trail. So we can all learn things, even if we've heard things before, and obviously they adapt as time goes. So thank you very much, June, for the time and effort you put into that. Thank you to all the students for attending, and we hope to see you at the next one, which I think is in a couple of weeks' time.
It is,
So
yeah.
thank you very much.
Well, thank you, and you always provide a very good audience. So excellent, thank you.